here's an interesting area problem. Find the area of the region bounded by x equals y squared plus 4y minus 22 and x equals 3y plus 8. Ah, what do you notice right away? Yeah, we've got some functions described in terms of y. So y is the independent variable here, and x is the dependent variable, the way this is written. Fascinating. So if we wanted to find the area between these two curves, could we use the strategy we learned recently? Meaning, could we make a whole bunch of vertical rectangles and imagine those vertical rectangles getting infinitely small, find the area of each of those rectangles and add them up using an integral? Yeah, we could, but it would be very cumbersome. We'd have to describe each of those in terms of x. We'd have to do a couple of integrals, right? The top part and the bottom part, the top part and the bottom. That would be possible, but very cumbersome. So why don't you pause the video and think of perhaps a less cumbersome way to find the area between these two curves. Yes, we're just going to embrace y as the independent variable. Instead of imagining making an infinite number of vertical rectangles, can't we imagine making an infinite number of horizontal rectangles? The way we'd find the area of the rectangle would be the same. It would be the length of the rectangle, which is, I guess it would be the right curve minus the left curve in this case, times the width of the rectangle, which is the infinitely small change in y. So we can call that dy. So we're going to find the area between these two curves, embracing y as the independent variable. Let's give it a whirl. Let's dive in. So I'm just going to draw one of these rectangles just so we can kind of visualize it. And again, the idea is we're imagining an infinite number of horizontal rectangles filling up this space, and then we'll use an integral to add up those infinite number of horizontal rectangles. So to find the area of each rectangle, it's the length, which is the right curve minus the left curve. I'm just going to write right minus the left. That's this distance. And then times the width of the rectangle, which is the change in y, dy. And we're going to do this, of course, on the correct integral. Now, if y is my independent variable, then I'm going to be finding the y values, right? What this y value is all the way up to this y value. You're stacking up all those horizontal rectangles from this y value of a, whatever it is, all the way up to this y value of b. And this is going to give you the area between the curves. So it's exactly what we did when x was our independent variable, but now y is our independent variable. So perhaps the first thing we should do is find the a and the b. We'll do it the same way. We can set those equal to each other. Y squared plus 4y minus 22 equals 3y plus 8. Can set that equal to 0, blah, blah, blah. And I think we will get negative 6 and y equals 5. Okay? Now, if you wanted to do this on your calculator, you certainly can. Students sometimes ask me when we're doing this, well, how do I put the y in the calculator? Well, you don't have to. I just put y equals x squared plus 4x minus 22. I put y equals 3x plus 8. I'm just looking for the intersection, so it doesn't matter to the calculator if I'm in terms of x or y. And then you will just do your second trace and find your intersections that way. Okay? All right. So we know that this lower bound is -6, and this upper bound here, whoops, I put the b in a funny place, is 5. Okay? So those are the upper bounds and the lower bounds. In other words, where these two intersected. Let's set up our integral. Here we go. To find the area between these two curves, it's going to be the integral from -6 to 5 of the right, so that's 3y plus 8, minus the left curve, y squared plus 4y minus 22, all with respect to y. Beautiful. Now, if you're doing this by hand, don't forget to distribute that negative, combine like terms, then you can take the antiderivative. You can do this in your calculator. If you're doing this in your calculator, the calculator doesn't really care if x is your independent variable or y is your independent variable. Obviously, the graph is going to look wrong, but it will find the integral just fine. From -6 to 5, I already put the functions in my calculator, so I think that first function I had under y2. Yep, that's right. So alpha trace gets me y2, minus alpha trace gets me y1. And we have a nice area of 221.83 repeating square units. That wasn't that bad at all. So let's say you had a scenario like this, where you had an implicit function where one of the functions is on the right for part of it, on the left for the other part of it. Well, you would set up your area similarly to how we set it up when we were doing it in terms of x. You'd break it up. So perhaps I'd say from a to b, right? My green function is on the right, my pink function is on the left, so it's right minus left, and then plus from b to c. Now my pink function's on the right, my green function's on the left, and again in terms of y. So same thing we did when we were dealing with functions in terms of x. If you have to break it up into different integrals, you can do that. But the bottom line is, we now can find the area between curves when they are described in terms of y, which is a really handy thing to be able to do.